Hello everyone, welcome to my YouTube channel. I'm starting a series of videos in which I will be solving problems from CSES problem set. In this series of videos, I will be solving particularly string algorithm set, and this is the first problem of that set. Okay, so let's solve this problem. The name of the problem is word combinations. In this problem, we are given a string of length n and a dictionary which contain k words, and we are supposed to find the number of ways in which the target string can be constructed from the given words. Okay, the input has the first line of the input contains the target string with n characters. The characters are between small a to small z. The second line has integer k, which represents the number of words in the dictionary. Finally, we have k lines, which describes the words. Each word is unique and they also consist of characters from small a to small z. The output will be the number of ways, and we have to print it modulo this prime number, which is 10 to the power 9 plus 7. Okay, let's see the constraints of the problem. The length of the target string goes up to 5000, while the number of words in the dictionary goes up to 10 to the power 5. Okay, let's see an example to better understand the problem statement. Okay, so this is the target string, and this is the dictionary that we have. Okay, it has 4 words and we want to construct this string using this dictionary. Okay, particularly this example has been taken from the problem statement, this example, and let's see the explanation for this. The ways to construct this string from the given words are these, namely using the word AB twice here, AB, and the word C once, right here. This is one of the ways. Another way is to use AB and C, right? This is another way. So there are total 2 ways to construct the string. Notice that I'm using AB 2 times here in this pattern. That means I can use a word multiple times to construct my target string. Fine. And the answer for this input set is 2. Okay, and which is indeed the output. So that's how we have to build our solution. Let's see how we can build the solution to solve this problem. Okay, the intuition to solve this problem is simple. We start from the first character, we start traversing the target string, and we check if the prefix that we currently have. So initially the prefix is a, then it will be ab, and so on. We need to check if the prefix that we currently holding is present in the dictionary or not. If it is present, then we have to find the number of ways to construct the remaining string. Let's see how it is done. So the first prefix is a, which is not present in the dictionary. Then we move to the next prefix ab. So I'm taking a dummy string str in which I'm storing my prefix. So initially it was a, now it is ab. I check if it is present in the dictionary. Yes, ab is present here. Then what I claim is that if I somehow find the number of ways to construct the remaining string abc, those will also be the ways to construct the entire string. Fine. How? Let's find out the number of ways to construct ABC. Well, there is only one way, that is to use AB and C. That will also contribute to the construction of the entire string, because all we have to do is to append AB before the pattern that we have got. Okay, so I will append AB, and I already know that AB is present in the dictionary. Okay, so that's the way to solve this problem. Then I move to the next prefix ABA. It is not present in the dictionary. Okay, I will move to the next prefix ABAB. Yes, it is present here. Then I want to find the number of ways to construct the remaining string, that is C. And there is only one way to do so. Just use this C. So here is the method to generate C from this dictionary. And what I have to do is to append my prefix which I have found that it is present in the dictionary, A B A B, and that is giving me another way to construct the target string. Fine. Then I move to the next prefix, that is ABABC, which is the entire string. It is not present in the dictionary, so I quit here. And the answer to my problem is 2, because I have found 2 ways to generate my target string from the given set of dictionary, from the given set of words, right? So that's how we solve this problem. You may have got the intuition of a recursive approach to solve this problem. Namely, once I found a prefix, all I have to do is to repeat the process for the remaining substring, right? So let's try to solve this problem using that approach. So imagine a function word combinations, right? It takes in the index of the string, okay, and returns the number of ways to construct the substring starting from that index to last index, right? So if I call the function from this index, then it will give me the ways to construct this substring, right? And to get the answer for our problem, we have to call this function on the first index here. So this function will return me the answer to the problem, right? How will this function look like from inside? We know that I construct prefixes, and if I get a prefix which is present in the dictionary, I repeat the process for the remaining substring, right? So the first matching prefix which I get is AB, and that is at index 1. Once I find that, I call the same function on the index 2. This will give me the ways to construct this string, which will contribute to the ways to construct the entire string. Fine. Then I find my next matching prefix at index 3. Here I call the function at index 4, which will give me the ways to construct the entire string. Okay, and that's all. I will add up the results of these functions, and that will give me the answer to the problem. The same procedure is repeated for these functions and so on. Fine. So how will the body of the function look like? So let's see. So this is how the function will look like. Okay, so this is how the function will look like. I have my target string dictionary, and here I have an answer variable initialized to 0, a empty string. This is used for storing the prefixes, and n is the length of the string. Now I use a while loop, and I run it until I reach the end of the target string. Okay, and I keep building my prefix. If the prefix is matching, that means it is present in the dictionary, that I am okay, that I am checking using a hash map. Here I'm using a hash map to check for the presence of a prefix in our dictionary, in our set of words. If it is present, then all I have to do is to call the function word combinations for the next index. Okay, the index for which I got a matching prefix, like here, get a matching prefix at 1. Then I have to call the function from index 2 here, right? And the result of that function will be added to the final result answer. So this is the final result, and then I increment my index by 1 and build the next prefix, match for the check for the next prefix, right? After I end up exhausting all the characters on the string, I return my answer. That's how the function looks like. But what is the terminating condition? Namely, what is the base case? So this is a recursive solution. How would I end my recursion, or what will be the base case? So imagine the scenario, imagine the worst case scenario in which I do not find even a single matching prefix in the dictionary, right? So let's say I don't have this dictionary, the dictionary is empty, okay? And in that case, I will simply I will never call this word combination function again. This function word combinations will be called exactly once, and this string will contain the entire target string after I end up this while loop, and answer will be 0. So I do not have to encounter the base case. Fine. But even if I find a single matching prefix, let's say AB, then this function will be called again. That means I will have at least two calls of word combination function. First at index 0, another at the index at which I find my matching prefix, right? So in that case, I have to encounter the base case, okay? And that means I have at least one way to construct the target string. Answer is not 0 in that case because I'm calling the function twice. That means I have found at least one matching prefix, and hence there is one way to construct this string from the given set of words. So that's why the base case will be 1 here. Okay, so that's the base case, and this is the hash map that I'm using for checking the presence of a prefix in my dictionary. So this hash map basically takes in the word of the dictionary, uses some using some hashing techniques, say rolling hash, and computes the hash value for the word and mark it as 1. This means that this means that this word is present in the dictionary. Okay, now this rolling hash works in linear time complexity. That means every time I check a prefix, every time I'm checking a prefix, that is costing me a linear time complexity for just to check if it is present in the dictionary or not. Okay, so let's analyze the time complexity for the entire code. So this is the recursive tree that I have drawn. I'm calling the function at first index. Okay, so imagine the worst case scenario in which for the target string target string was ABC. So this is the worst case scenario which I'm using for analyzing the time complexity of the code which I shown you in the previous slide. So the worst case is that in the dictionary I contain every substring. Okay, so I contain A, B, C, A, B, B, A, B, C, A, B, A. Okay, then I have B, A, B, A, B, C, A, B, A, B, and the entire string itself. Okay, in that case, the word combination function will be called at each index. So first I'm calling it at index 0, then that function in turn will call the same function at index 1 here. It will call it at B. It will call it at recursive call will be again made at index 2, index 3, 4, and so on. And for the function which is called at index 1, the same procedure will repeat. Okay, so at the first level you can see at this level I'm just calling the function once. At the first level, the number of calls made to the word combination function is n minus 1. And in the next level, WC1 is calling the function n minus 2 times. This is calling the function n minus 3 times. This is calling the function n minus 4 times, and so on. And there are n minus 1 such terms. Fine. So if I add them, that is giving me a roughly n square function calls at each level. Okay, and the height of the tree is n. How? Observe this branch WC 0, 1, 2, 3, 4, and it will go up until the last index, which is 4 indeed. Fine. So that's why the height of the tree is roughly n. So the number of function calls will be n square raised to the power n. Why? Because we know that the branching factor is roughly n square, while the height of the tree is n. Therefore, number of function calls will be roughly n raised to the power n. Okay, so only the recursive code is giving me the time complexity of n raised to the power n. So but there is another thing here, that is this map. Every time I am checking for a prefix, I have to use this map, which is taking linear time complexity, and I have to check for each prefix, right? I have to check for AB, ABA, ABAB, AB, ABC. Then I have to check for B, BA, BAB, BABC, and similarly for the rest of the indices. Fine. So that is giving that means I have to check for each prefix. Hence, it will also contribute a time complexity of big of n raised to the power n. The time complexity for the map is evaluated. Fine. So the overall time complexity becomes n raised to the power n plus n raised to the power n, which is n raised to the power n. Fine. And this is very bad time complexity, because even for a small input of size, say 10, a string containing 10 characters, the time complexity will be 10 raised to the power 10. And you see the number of iterations a computer makes in a second is 10 raised to the power 8, and hence it will take almost 100 seconds. Okay, so this will throw TLE. Okay, and it is not going to work for the current problem here, 5000. So it will not work for a string of length 5000. Okay, if you want to learn more about rolling hash, how this hash map implements rolling hash, then you can go to CP algorithms. I'll attach the link in the description, so make sure to check it out. So after analyzing time complexity, we know that a recursive code can be converted into a memoized code. Fine. Like in this recursive tree, we know that some results are computed again and again. For instance, this this WC2 is called here and here. Okay, so it is called twice here. WC3 is called here, it is called here again, here again. Okay, and here. So the computation is repeating. So rather than doing so, what we can do is to memoize the given code. What is memoization? Is that whatever the results are computed at any index, for instance, the function WC11 will give me the results for the string BABC. Fine. And if I store that result in an array, then I do not have to compute the result again. Fine. Similarly, I do for all the indices, so that this subtree is not repeated. So I have results stored in my array, and whenever I require the result, I simply have to check if it is present in the array, and if it is present, then I will return the result. Fine. For that, I'm using a DP array which has a length of same as the length of the string plus 1. Plus 1 is taken so as to store the base case value. Fine. And I will initialize the DP array with -1, because this is used to check if the result for the particular index is computed or not. If -1 is present in the array, that means the result is not computed yet. If it is not present, that means I have already made the computations required. So here you see in this code, the changes that I have made is simply, if I reach the base case, then I will assign 1 to the last index here. If I already have the result for some particular index, that means if I do not have, this is not equal to -1, if I do not have -1 or rather some other integer, then I will return that result right from here. Otherwise, I have to make the computations which I made in the previous code. And after I made the computations, I will store that answer for that index in the DP array that I have. Okay, so that will reduce the unnecessary computations which are being done here. WC3, this will be eliminated, and WC3 will be computed exactly once. Same goes for the other indices. Fine. How the time complexity will be enhanced using the approach that I have explained here. So you see, what I am doing after memoization, I know that this function will be computed exactly once for each index. That will reduce the time complexity to big O of n, while the space complexity will increase from constant to big O of n. It was constant before, but now it is linear. Fine. In recursive code, we do not use extra space, but stack space is consumed, which is used for storing the function calls. Fine. But here I am storing the results in the DP array, so the space complexity becomes linear. But what is the overall time complexity of this code? It is still n raised to the power n. Why? Because notice that I'm still using the map. So because of the map, I have the time complexity big of n raised to the power n. So this code is also not going to work for the constraints. Fine. So how will I replace the hash map? So I require some other data structure which I can use instead of hash map, which do not use linear time complexity for checking the presence of a word in the dictionary. And we know that another data structure similar to map for checking the presence of words in the dictionary in an optimal way is trie. So what is a trie? A trie is a data structure where the nodes of a tree, it's a tree like data structure basically, and the nodes of that tree stores the letters of the alphabet. Okay, so how does a particular node of a trie looks like? A typical node of a trie looks like, so this is how it looks like. A trie node, it contains 27 slots which are made for 27 letters of the alphabet, of small alphabet, and that's all. That's a trie node, and a set of such trie nodes is what we call a trie data structure. Okay, so let's see how we can use this trie data structure to optimize the solution that we have. So here you see that this is a typical trie data structure. It has a set of some nodes 0, 1, 2, 3. So these are nodes of the trie, and we use another array in trie data structure is end. This particular array is used to mark the end of the word. So whatever the word we are inserting in the trie, to mark the end of the word, we use this node, we use this array. Fine. So how do we implement this data structure practically? So it is easy. All I have to do is simply declare the trie data structure as an array and specify the size m, and each node consists of 26 slots for storing the small alphabets, small letters of the alphabet. And this is easy. I have to assign, I just declare an array of size m. So what is m here? How will determine the m? M simply depends upon the largest size of the word that we want to insert. Okay, so whatever the set of words we have, find out the largest word that we have in that set, and whatever the length the word have will be the length, will be the number of nodes that we require in the trie. Okay, so that's how we implement trie. Let's see how this can help us. Before that, let's understand the operations that we have to perform, that we can perform in a trie. Okay, how basic operations work in a trie, what is the time complexity of the operations. Okay, so there are namely two operations, insert and search. This function is used to insert a word in the trie, in this trie data structure, while this function is used to search for a word in this in the trie. Okay, so let's see how insert works. Okay, so this is trie, and this is how an insert function looks like. It first of all, I declare a counter variable, initialize it with 0. Then inside the insert function, I use a current variable, it is initialized to 0. I iterate over the word which I want to insert. Let's say I want to insert AB. Then I iterate over the word. So I am standing at the first character of the word, and current is 0. So this if the first trie node at this particular character is filled or not, and we know that this is empty, so this condition is true, it is not filled. So we assign counter to this node. So I assign 1 here. I increment my counter by 1 and I assign it here. Okay, so why I am incrementing? Just to jump to the next node. It simply says that yes, A is present here, move to the next node of the trie to check for your next character. Fine. So now the current is at this node. Current is pointing to 1. Okay. Now here I see that I'm standing at character B, and I check if B is present here or not. Yes, B is not present. So I increment my counter by 1 and assign and mark B with 2. It simply says, okay, B is present here. If you want to find the next character, then move to the next node. That's what this 2 is saying. Fine. And I move my current to node 2. So current is here. But that's all. I have exhausted my word. Then I break out of this loop and I mark is and to be 1. This says that whatever the current is, that is 2, I mark it 1 here in this array. It says that yes, I have reached the end of the word at node 2. So, so that if I am here to search for this word, then I can make sure that yes, B is the last character. Fine. So that's why this array is used. So I marked 2 as 1 because it is the end of this word. So that's how this insert function is working. And the time complexity of this function is big of k, where k is the length of the word that I want to insert. Okay, let's see the another operation, which is the search operation. How search operation works in the trie. So I have, from the previous slide, I have 1 and 2 stored here, and 2 is marked 1 here. So how would I search for a word in the trie? So let's say I want to search for AB, the word which I inserted in the previous case. So I initialize my node with 0. I iterate over the word. I check if the particular character that I'm standing. So initially I'm standing at A, and the node is pointing to this this node variable is pointing to this node of the trie, and I check if A is present in this node or not. Yes, A is present because it is marked here. So if it is present, then jump to the node which it is pointing. So it is pointing to 1. That means it's saying yes, A is present, move to the node number 1. So now the node is pointing to this node. So node variable is here. And here I switch to the next character B. Okay, and I check if B is present in this node or not. Yes, it is present. So B is present here. It says that yes, B is present here. If you want to find the next character of your string, move to the node number 2. Okay, but we know that this is the end of the word which we are searching. That means I break out of this loop. Fine, but how would I check if I have found the word or not? Using this array. That's why I marked the array is end by 1. So I see 2 is marked 1. That means yes, the word which I am giving as an argument is present in the trie, and the answer will be yes or true. I have found the word. That's how the basic operations of a trie works. The time complexity for this operation is also big of k, where k is the length of the word. Okay, let's see how this will help us solve the problem that we have. So we have to modify this search function to solve our problem. So let's see the so here in this function, how would I modify that? So I will simply, instead of performing this check again and again, what I will do, I will simply use the is and array, the array which I declared here, to check if a particular prefix is present in the dictionary or not. That means, for instance, if I find the prefix, say AB, let's say I'm iterating over the prefix, I find that B is marked true in the is and array. So in my is and array, this index is marked 1. That means yes, AB has been inserted into the trie, which is only possible if I insert it from the dictionary. Okay, so the idea is to simply prepare the trie from the given dictionary of the problem, then iterate over the prefixes and check if a particular character marks the end of the word. So if B is the end, that means I have already inserted that word from the dictionary. Hence I have to call the function from the next index. So this will reduce the work which is done by the map here. Let's see how. Okay, so this is the final word combinations function, which is using trie data structure instead of hash map. In this function, what I am doing is I'm initializing a node with 0. So node is standing at the first node of the trie. It represents the it basically points to the nodes of the trie, and the trie is already prepared. That means the dictionary that we have given in the question, the dictionary has already been inserted in the trie. So I have inserted the word AB only. Okay, so this word is inserted. Now I simply iterate from the given index in this function. Let's say I call the function word combinations at index 0. Okay, So I call this function at index 0, and the node is pointing to the first node of the trie. I check if the particular character of that node, namely the first character is A and the node is 0, if that character is not marked, that means this is not present in the trie. If it is the case, then I simply return from there, because I've got that yes, that is not, this character is not present. For instance, if I start from B, so let's say the function is called at wc1 and node is initialized to 0. I see in the node 0 B is unmarked. So B is unmarked, that means there is no word that I have inserted in the trie which starts from the character B, and that's why I return the answer which I have already computed after I store it in the DP array for the sake of memoization. Okay, fine. But since I'm starting from the character A and I know in the node 0 A is present, A is marked true here. So that's why I move my node to the node which this node is pointing. Okay, so this is pointing that okay, A is present. Now you move to the next node, node number 1, to check for your next character. The next character is B. Okay, so I check if B is there. Yes, in the node B is also marked. So it is saying okay, B is marked, you can move to the next character. So here node is 2 now. So node has become 2. And here I am checking if this node is marked 1 in the isEnd array. Yes, it is marked. That means AB is present. Okay, AB is present, and I have to find the number of ways to construct the remaining string. And in that, here in this line, that's what I'm checking. If the result for this substring is already computed, then I return that result. I add that result in my answer. Otherwise, I call the function for that index and add the answer in my final answer. Okay. After I have computed this for the entire string, the target string, I store the answer for that particular index and I return uh, from here. Okay, so that's how this function is working. I hope you're getting the idea how this trie is helping us to check for the prefixes. So what is the time complexity? Let's analyze the time complexity for this particular code. Okay, in this code I am not using hash map. I do not have to first build the prefix and then use hashing to find if the hash of that particular prefix is present in the hash map or not. That was taking a linear time complexity. I am just checking if the end of the current prefix is marked in this array or not. If it is marked, that means it was inserted. If it is not marked, that means it was not inserted. So this is what I am reducing here. So let's understand this using an example. For instance, this is the target string. I'm calling the function at index 0, and this function will call the function at index 2 because I find that yes, AB is present. Then I will call the function at this index, and this function, the function that I am calling here, this will call the function at index 4. So this is calling the function at index 4. Okay, so this will return me 1. This will return me 1. So the result for this is 1. When I come to this prefix ABA is not marked because it is not there. AB is there, so this is marked as the end, node number 4 or node number 3. So that means ABA was inserted, and that's why I would like to call the function at index 4, but I have already memoized the result for that. So this will not be called. Instead, 1 will directly be returned from the DP array. Fine, 1 is returned from here, 1 is returned from here. The answer, I will add them and the answer will be 2, and that's the answer for the problem. So you notice the time complexity is simply linear. Okay, but the space complexity using the tries is has increased to go of n into 26 because there are 26 slots for each node, which is same as big of n, plus a linear time complexity for the is and array, which is again big of n. So that's how I reduce my time complexity to linear time complexity. This will work fine for the constraints of this problem. Okay, so let me show you the code implementation of this problem. Okay, so this is the code implementation for the problem that we are solving in C++ language. This is an insert function. So first I am taking in the dictionary and I am inserting the dictionary in the trie. I have declared my trie here. Okay, so then I'm declaring a DP array. I have declared the DP array globally and I'm initializing it with -1, and I'm calling the word combination function at index 0, which is the starting index of the target string here, and this function is performing the computations. While for memoization I use this array, fine, and the results are computed using the mod, that is 10 to the power 9 plus 7, which is given in the problem statement here. Okay, let's see the implementation in in Java language. Okay, so this is the implementation in Java, and this is the implementation in Python. Okay, so that's all from my side. I hope you understood the problem. If you have any question, then make sure to post in the comments, and I have attached the code in the description of the video, so make sure to check it out as well.